Hi everyone, I'm Mr. Fullerton, and today we're going to talk about standing waves. Our objectives are going to be to describe the formation of standing waves and to determine the number of nodes and antinodes in a standing wave. So let's start off by talking about what a standing wave is. Waves that have the same frequency and amplitude traveling in opposite directions can produce a standing wave. Got to have the same frequency, same amplitude, and travel in opposite directions. Now, certain points on a standing wave appear to be standing still, and other points, known as antinodes, vibrate with maximum amplitude above and below the axis. So certain points that appear to be standing still are things like these nodes, and as you can see, there are 4 nodes on this standing wave. Antinodes vibrate with maximum amplitude. There are 1, 2, 3 antinodes. Notice that even though you can see another antinode position up above there, because the wave is only in one of those positions at any given time, you don't count it twice. There's always one less antinode than node, or one more node than antinode. Now, these are very, very common when you talk about musical instruments. Just about any musical instrument you can think of depend upon standing waves to function. Guitar strings, for example, they demonstrate a standing wave pattern. When you fret the strings, you actually adjust the wavelength of the string, and therefore the frequency of the standing wave pattern, and therefore the pitch. You could also see a very similar functioning when you talk about pianos, drums, flutes, trombones, xylophones, pipe organs, even harps. All of these instruments function on the concept of standing waves. So if we look at a sample problem here, while playing, 2 children create a standing wave in a rope. A third child participates by jumping the rope. What is the wavelength of the standing wave? Well, if you look at it, we're seeing half of a wavelength here, right? An entire wave would follow through like that. So if half the wavelength is 4.3 meters, then the wavelength itself must be 2 times that, or 8.6 meters, right from the picture. It's another example. If wave X travels east with frequency F and amplitude A, wave Y, traveling in the same medium, interacts with wave X to produce a standing wave. What statement is true about wave Y? Well, we know if it's going to create a standing wave, it has to have the same frequency, the same amplitude, and be traveling in the opposite direction. So, must have a frequency of F, choices 1 and 4, an amplitude of A, choices 1 and 4, and has to be traveling in the opposite direction. So its direction has to be west. The correct answer must be 4. To produce a standing wave, you need 2 waves with the same frequency, amplitude, and traveling in opposite directions in the same medium. Here we have a diagram showing a standing wave. Point A on the standing wave is a node or an antinode. Well, if you recall here, nodes are the ones that don't move at all, so this must be a node. That eliminates choices 3 and 4. And what does it result from here? Well, it results from destructive interference. Because we're going to 0 amplitude, that's a destructive interference point. So the correct answer must be 2, a node resulting from destructive interference. One last problem here. One end of a rope is attached to a variable speed drill, and the other end is attached to a 5-kilogram mass. The rope is draped over a hook on a wall opposite the drill. When the drill rotates at a frequency of 20 hertz, standing waves of the same frequency are set up in the rope. We're at first asked to determine the wavelength of the waves producing the standing wave pattern. Well, if I look at the diagram, I can see that I have 1 full wavelength between the drill and the wall. So if that wavelength is 3 meters, this becomes a very simple problem. Wavelength lambda is 3.0 meters. Now, to calculate the speed of the wave in the rope, we have to go back to our wave equation. Remember, velocity equals frequency times wavelength. Our frequency is 20 hertz, and our wavelength here we just determined was 3 meters. Therefore, our velocity must be 20 times 3, or 60 meters per second. Hopefully that gets you started with standing waves. If you have questions, need more help, visit APlusPhysics.com. Thanks, and have a terrific day.